Okay, so you are given a text and a pattern. Text is of size n, pattern is of size m. You want to find the location of the first occurrence of the pattern in the text. So these have different sizes, right? See, one simple idea is if m is greater than n, then definitely pattern is not inside the text, right? You can say, it doesn't exist. Okay, so we assume that m is less than or equal to n. Okay, so as I was saying before, one application is Google search. Suppose you search for a keyword elephant and you got a web page. There might be multiple occurrences of elephant in that web page. You want to find, say, all occurrences or the locations of all occurrences. Think about your text editor also, where you search for a keyword and automatically it will show you all 117 occurrences of that pattern. If you replace all those will be replaced, right? What's that? It's string matching. You're really using a string matching algorithm, right? So it might be working with text editors, or it might be Google search, and so on. It's a very fundamental basic problem. Okay, let's look at a very naive approach, exhaustive search. So how does this exhaustive search work? See, this is your text T, and suppose this is the pattern P. What does the exhaustive search say? Try all possible combinations and find out the valid solutions, right? Print the valid solutions, right? What is the idea? Compare all characters of pattern, right? Say there are m characters, right? M characters of the pattern with first m characters of the text, right? If they match, then say that your first occurrence of the pattern is 0. Else, shift the pattern by 1 unit. Now compare all characters of the pattern with m characters of the text starting from 1. If they match, see, all characters should match. Then you say that the first occurrence of the pattern in the text is 1, and you exit and you return. Suppose the pattern did not match anywhere. I mean, either it might be the first character itself or in the last character. It can be anywhere, right? Shift again. So keep doing it until, can you tell me what is the last case? What is the last case?
You reached
And
m, yeah, minus m.
Go ahead, Edward. Yeah, go ahead.
Sorry.
No, it's okay. Go ahead.
Go ahead. You go ahead.
I was gonna say n minus m.
Right, n minus m. N minus m. Right? So you check if pattern matches with the last m characters here. M characters here. Right? This is the worst case. All this is failed. Now this is the last matching criteria you're checking for. If this fails, then you say that the pattern does not exist. Right? So this is your exhaustive search. Now, can you tell me in this search space, what are the candidate solutions? This is a candidate solution. This string is a candidate solution. This string is a candidate solution, so on, right? So how many candidate solutions are there? Approximately n minus m. You need to check whether it is plus or minus 1 or something like that, right? Approximately n minus m candidate solutions. Then what is a valid solution here? The valid solution is the first occurrence where the pattern matches the text. Suppose we change the question to find all occurrences of the pattern matching with text, then what are the candidate solutions? All occurrences where the pattern matches with that substring of the text. Make sense?
Yes.
That's your exhaustive search algorithm, right? See, check if the pattern matches with the text starting from the first index. Else, check if the pattern matches with the second index of the text, right? Onwards, so on. See, here is the pseudocode. So what do we do? I starts from 0 to m. And we know why this is the case. The starting index is 0, next is 1, so on up till n minus m. We cannot go past this, because if you go past this, the pattern will be outside, right? So this is the last entry. Okay. Now, this logic is all about pattern matching, right? So J is equal to 0. J represents, you can say, the number of characters, right? Matched with characters of pattern that matches with the text. Okay. So while J is less than M and P of J is equal to T of J, right? See, the idea is this. So J is equal to 0 initially. 0 of pattern is I plus 0. Okay, let me show you a generic comparison only, right? Suppose you are starting with the ith index of text. Now J is equal to 0, J is equal to 1, right? All these are indices in the pattern up till J is equal to m minus 1. J is equal to 0, J is less than m, and P of J matches with T of I plus J. I plus 0 is this, I plus 0 is this, I plus 1 is this, I plus 2 is this, so on up till I plus m minus 1 is this, right? Characters of text, and this is J, J is equal to 0, J is equal to 1, so on. So this is P of 0, P of 1, P of 2, so on up till P of m minus 1. And what about this? This is T of I, this is T of I plus 1, this is T of I plus 2, so on up till T of I plus m minus 1. You keep comparing this and this character, right, in a loop. Okay, and keep incrementing J. Once you come out of the loop, it can be for two reasons. What are the two reasons? The pattern matched or the pattern does not match. If J is equal to M, that means the index went beyond this. It went beyond m minus 1, right? So this means there is a pattern match. Pattern match. The pattern match starting from the ith index of the text, so you return I. If the pattern did not match, you don't care. You continue in this loop. You will go to the next index of the text and continue pattern matching, right? If the pattern did not match, you do not care. You continue in the text with the next index. But if the pattern matched, that's it. You just want the first position for the pattern match, right? You return that index and stop. Done. Finally, if after this there was no pattern matching, you will return minus 1. Minus 1 represents there was no pattern in the text. So does this make sense?
Yes.
Okay, so any questions here? Can you tell me what happens when m is greater than n?
You'll probably get an array out of bounds error.
No, you don't get into this for
Why?
Oh, you're right.
because you will compare, right? The I will be less than this, right? Less than
Exactly.
something. Yeah.
If n minus m,
This is negative.
okay, if m is greater than n, n minus m is what?
It's
Less than
negative.
Yeah.
0, right? That is negative. Hence, it will not go into this for loop to
Right.
return -1. Make sense? Okay, so that's about it. That's your exhaustive search. But as I said, exhaustive search, right, typically will be the slowest algorithms. But that's the starting point of coming up with algorithms, right? Okay, see, brute force solution takes mn time here. In the worst case, all this is the worst case, right? Space is m plus n for the input. Pre-processing time, there is none. But see, there are so many other solutions that are much faster. And Rabin Corp is also good, though the worst case time is mn, but in practice, it runs a lot better. Boyer-Moore also, right? Okay, anyway, so we will not go into all this. I just want to show you that, see, it's not just about, see, for coding, you need to understand what these algorithms, right? See, trie is a complicated data structure that uses a tree. This is also a suffix tree builds on top of trie. Rabin-Karp algorithm is another beautiful algorithm that uses hashing. Aho-Korosik algorithm uses finite automata. Boyer-Moore KMP algorithms are, you know, are use some beautiful ideas of their own, right? Anyway, see, there are so many complicated and beautiful algorithms. I mean, not all are complicated. Rabin-Karp, Aho-Korosik, Boyer-Moore are relatively much simpler algorithms, right? Even trie is also relatively simple algorithm. Anyway, so all these are out of scope, but I just wanted to show you the beauty of algorithms. Okay, next, closest pair. We will cover just this problem and stop, right? We do not have enough time. So given n points in 2D Euclidean space, you want to find the closest pair of points. So what is 2D Euclidean space? It's a 2D space like this. You want to find the closest pair of points. Maybe this is the closest pair of points, right? This is the closest pair because the 2D Euclidean distance between them is minimum among every other distance between 2 points. See, if there are n points, can you tell me how many line segments can you make?
Oh,
Huh?
let's say n2.
N choose 2, right? N
Yeah.
choose 2 is the total number of line segments you can make, right? Among all these, you are picking one that has the minimum distance, Euclidean distance, or you can just say closest pair, right? So that's your problem. And what is the simplest exhaustive search? So
Go through each point and find the distance to every other point and compare them.
exactly. Or you can just say for every pair of points, right? Find the distance, and you can and you find the min distance among all these distances, right? So I will not give the code here. Find the min distance among all these distances. That's your answer, right? So all these are the candidate solutions, and this is the valid solution. The pair which has this min distance is the valid solution, right? Okay, so let's directly go to the code. Closest pair, you're given the x coordinates, you're given the y coordinates, n x coordinates, n y coordinates. You want to find the closest pair of points A and B. I mean, you can also give the distance, but we are specifically finding out the pair itself. Okay, minimum is infinity. Then you have two for loops. One for loop for the first point, second for loop for the second point. Now, can you tell me why do we have this I plus 1 to n? Why not 1 to n?
You don't compare to yourself, right?
Right.
Okay, why not 1 to n and then remove, I mean, the same points.
It's say not P, right? So it's not commutation, it's just combining. So each time you pick one, you don't visit again to pick another, right? Because J is same as Ji.
Good. See, one can write a for loop like this. I is equal to 1 to n. Then for loop J is equal to 1 to n, right? And apply the logic. This also works, but this is slightly better. The reason is, as you said, you don't care for this point, I comma I. And not just that, you don't care for, suppose you have computed the distance from I to J, you don't want to compute the distance from J to I because it is the same, right? Redundant computations. So hence, we order that J is always greater than I. It should always be greater than I. Okay, and distance is, apply the Euclidean formula to find the distance. If distance is minimum distance, so you find the min distance. Whenever you find the min distance, you store those points. The points are, say, the index number, right? A is I, B is J, and at the end of this, you will have stored those indices. So just return XA, X coordinate of A, Y coordinate of A, X coordinate of B, Y coordinate of B. That's it. Make sense? Right? So this is your exhaustive search. You try all possible combinations and pick the valid solution. And see, as I said earlier, always your exhaustive search, right, will be slower. You can do much better. But this is often the first idea that one comes up with, right? See, there is a divide and conquer algorithm that can solve the problem in n log squared n time. And there is one more improved algorithm on top of it that can reduce the time further to n log n. And this is currently the best known algorithm to solve the problem, n log n. It's beautiful, right? See, there is a polynomial improvement. This is, as you must know by now, that if you plot, this is n squared, right? See, this is n squared. This is n log n might be something like this. N log n. It's like n, right? It's very near to n, but maybe slightly higher than that. Slightly higher than that. Right? N log n is approximately similar to n, you can think, right? But multiplied by log n is a tiny factor. But look at n squared. N squared grows like this. So the improvement is vast. It's amazing, right? See, the beauty of algorithms is like this. You can polynomially improve over naive straightforward algorithms. Okay, we will stop here and we will continue in the next session. Okay, so